My name is Achal Shah. I hope you can hear me fine. I'm going to be talking about Tecton's journey to the promised future and back, and how we evolved some of our real-time compute infrastructure. For context, I'm the tech lead manager at Tecton that leads the real-time compute team. This is basically the work that my team has been working on over the past 2 years or so, maybe a little bit more. So let's get into it. As by way of agenda, I'm going to talk kind of briefly about what Tecton is, what real-time compute means in the context of Tecton, our first iteration of how we built the solution that we ran in production for a while, um, some of the themes that we saw, and how we evolved this along the way. So, introduction, what is Tecton? Tecton is an AI data platform, and what this means is that it makes it easy for you to use your existing data for deploying machine learning models. Um, and it does so by making your data available, operationalize is it your data for generating training data sets, making it available for inference at low latency and at high scale. And it works for both predictive and generative AI applications. And so what problem does this solve for customers? So combining batch and real-time data is challenging to say the least. You need to model data correctly because you need to make sure that you're not leaking labels all over the place, or that you're not performing time travel on your features. And obviously this has to work at like a wide range of scale. Some of our users are using Tecton to serve at multiple thousands QPS, and they're generating training data sets of the size of multiple petabytes. So these are challenges that are as such undifferentiated if you're like a large organization, but there's something that we're uniquely suited to solve. So architecturally, what does this look like? Imagine that you have batch data somewhere in Snowflake, maybe in Redshift, and you have real-time data. And this real-time data on your end somehow is getting into your, data warehouse or your data lake. And your real-time data can be something like in Kinesis or Kafka, depending on how you set up the infrastructure internally. What Tecton does is it can spin up these materialization jobs for you. And what that basically means is that it can read data from your batch data sources or your stream data sources, and it can perform a number of different kinds of operations on this set data. So you can filter stuff, you can transform stuff, you can perform aggregations, things like that. And ultimately, all of this ends up in the Tecton offline and online store. So the offline store is how we store data for historical data retrieval, and the online store essentially only contains the latest feature values for whatever data that we've processed recently. And so once you have all this data in these two stores, you'll notice that there is a challenge to make sure that you are maintaining this like online offline consistency across the two stores. And then when you're generating like historical training data sets, you use our SDK to query the offline store using like an API called get features for events. And you can read the latest feature values from the online store using a feature serving endpoint. And this is what you would use if you have like a real-time application that's deployed in production. So an example would be you're trying to make like a fraud decision on a transaction. You need to get the latest feature values for both a merchant and a user that is trying to perform a transaction. This is the endpoint that you would typically query. So like typically you end up with like a client application that's going to make a post endpoint to a post call to an endpoint that we own and we scale for customers, which directly queries this online store. There are other components to Tecton that I'm not really going to be touching on this talk, because there's the SDK, as I mentioned previously. It contains a declarative feature definition framework. So the nice thing about the way that we uh, have users define their feature transformations is that the pipelines are kind of set up declaratively based on configuration, as opposed to users having to get a lot of the pipeline programming logic correct. There's also a web UI that lets you discover features and potentially reuse features. There's Python and Java clients for that wrap our HTTP API, so you can not have to rebuild clients for these languages from scratch. And there's other stuff also that I won't be getting into. So let's zoom in on this part, because that's where real-time compute comes in. So there's the Tecton feature serving endpoint. Your client application makes request, gets back responses. Now, one of Tecton's core product capabilities is to run user-defined and user-specified Python code on data. For example, users may want to pre-process incoming events from, say, either a batch source or a stream source before it is persisted in the Tecton store. Another thing that we might want to do is you might want to post-process this data that is being returned by the online retrieval system, maybe combine it with request time data. And there are potentially other newer product capabilities that we do want to invest in that might require us accepting some kind of user code that we execute on their behalf. So this thing that I showed you earlier, what this actually looks like is more like this. So essentially you have some online data in the online store, which is read by the feature serving endpoint. And then feature transformations or all of this user compute, this real-time compute, which is typically defined as Python transformations. This is executed somewhere in our feature serving endpoint in that service. And so it manipulates or munges the online data that's been read. And that is the thing that is actually returned to customers. So I'll put the question to you without belaboring it, but take a second to think about how you would have to build something like this, keeping in mind the things that we want to promise and deliver for customers, which is it has to scale, it has to be secure, because we want to make sure that we're not allowing like data exfiltration or like credentials to be lost or anything like that. It also has to be cheap. Cheap in the sense that it has to be as cheap as possible to still give you scale and security, but not any cheaper. And theoretically, you also want it to be flexible because when you give users the ability to write and execute their own code, typically they want to be able to do the same things that they can on any other cloud environment. So third-party dependencies, all kinds of configuration that they may want to tweak about the code that is actually running. So this is where real-time compute for Tecton comes in. So I'm going to talk about V1. The first attempt that we built was actually built pretty scrappily. We built it over the course of a very short number of weeks in response to a customer who came to us and said, hey, this is the thing I want to do. And we said, that makes sense. It should be something that you could do in Tecton. And the way that we built this is like the first version, extremely scrappy. You just run a Python subprocess alongside the high performance Golang based retrieval system. So the Tecton online retrieval system that I showed earlier is essentially a Go service that we run on Kubernetes. And so we change stuff so that the service when it starts up, starts a Python subprocess. And for any kind of like real-time compute that has to happen, it sends all of the necessary data to this like subprocess that's essentially a gRPC server that's listening over socket. So what this basically looks like is you have like this one feature server container, which is the Go-based feature server. And inside it, within it embedded is like a Python interpreter, which is where all of your real-time compute happens. So it's like essentially the sidecar pattern that we've kind of known and love for a variety of other use cases. So what worked well? Solution was like extremely simple for us to ship. It was relatively easy to add into the system without it being like a huge change to the data model, and it just worked. And the proof was customers actually started to get a lot of value out of these post-processing capabilities. I talked about all of the stuff in the context of the online retrieval system, but with a few changes, we could also do the same thing offline. And so now you have this ability of like embedding all of these transformations inside of Tecton and then them running consistently online and offline, which is great for customers because it's a single pane of glass for them to be able to view all of the stuff that is running. And it was actually generally performant, like latencies were relatively low. And so for like simple transformations, you would be able to execute them in a matter of a few milliseconds. More complicated ones, it really varied on the complexity of the actual code that you were running and the amount of data that it was processing, but it wasn't, there wasn't a lot of overhead involved. But pretty soon, Seam started to show. As you can imagine, the current architecture, the one that we're discussing, there's extremely tight coupling. And the tight coupling is between the Go-based feature server and the Python-based real-time compute server. And this tight coupling meant that you couldn't scale these two things independently. So now we all have heard a lot of stuff about Python and its general lack of performance in high scale systems. And this is kind of true because if you're comparing like a single like sufficiently provisioned Go-based feature server that is basically doing a bunch of I/O, it can actually go through a lot more requests per second than a Python service at the same scale that is trying to attempt to service the same kind of requests. And so for compute-heavy workloads, it's basically a waste of resources and money because you'd have had to passively over-provision the number of feature server pods that you had running. The other seam was the Python environment that users were expecting to run their code on. It was essentially like baked into our service container image, and it was locked down and completely controlled by Tecton. And it wasn't something that we were equipped to let users manipulate in any way. And so the idea of bringing in third-party libraries was not going to happen. The idea of bringing in like first-party libraries where users bring in like their own libraries from their private Python repos, impossible. The other thing here is, the Tecton code that does run had relatively low privileges, nothing that the user code could potentially manipulate. But on principle, it's like a bad idea to have user code and Tecton code run like the same permission sets. You want them to be able to run different permission sets. The other thing is users needed to write purely functional code because this code was executed in its entirety for every single request that they sent to the online retrieval system. And so while this was simple, not all use cases work best in this way. Some state can actually be good across requests. For example, if you instantiate a client once, maybe you don't want to instantiate it every single time for every single request that is coming through. For example, models, and you can't load a model for every single request. That's going to be too slow. And then this one is a little bit in the weeds, but the current implementation involved loading code, user code dynamically. And if any of you have done something like this with Python, you know that there's like a lot of fragility in how that potentially can work. And it was tricky to maintain backwards compatibility when there was no like strict interface that users could expect. And so let's talk about serverless. What is the serverless thing? Big picture, the promise of serverless is you run your code in response to events without requiring any kind of provisioning or management of servers. Most serverless solutions offerings, they model user code as functions, pure functions potentially, and they can be invoked synchronously or asynchronously. Some of these examples are actually well known to most folks, I imagine, which is AWS Lambda or Google Cloud Functions. And so when we were noodling on what is something that we can do to actually alleviate some of the seams that we're seeing in the first iteration of the stack, one of the key ideas that we kind of congealed on was let's run this user code as an AWS Lambda function. And we picked AWS Lambda because Tecton is cloud native and it's like AWS first. So it made the most sense and had the least friction to actually get started that way. And so in principle, this is great, right? Because you have independent scaling because Lambda will just scale up the number of like concurrent executions of your function as needed. You don't have to worry about it. You can't worry about it because you have no knobs. And there's no cost if there's no usage. So you can create and provision a function, but it's not running if it's not executing. You're not paying any cost for it, which is great. There's zero ops. And so customers also don't have to like configure anything on Tecton to say, I need to have at least this much provisioned ahead of time. You can also create like multiple functions for users with like different dependencies. And so imagine in your organization, you have some folks who use like multiple different versions of like some library. You can now create like these different environments and you can specify the kind of routing to happen at like query time to make sure that you can actually live in this world where you have multiple conflicting dependencies. It's super flexible. This also solves the problem of security because you can now run with a much less privileged IAM role, which means that user code basically has like completely locked down and has no access to anything. And so the other thing that you could do is we released the Tecton runtime code, the thing that is actually like loading up user code dynamically as a library. And this makes the interface extremely strong because it's like fully versioned. It's available on PyPy. Users can inspect it and they can figure out what's wrong, which is great. And so if you go back to the slide that I had, essentially what happened is we now have this new call path that is possible where your Go-based feature server can now invoke functions on AWS Lambda, and it does more or less the same thing. And this environment-based routing that I was showing you is essentially an example of how you could do this with like multiple different dependencies. You could just say, this is the name of the environment that I want to use for this feature service. And so the routing would then send like the transformation request to this particular environment instead of a different environment. Pretty simple. But what is the reality? Again, seams started to show relatively quickly. First one is cold starts. It's very difficult to avoid. You practically cannot avoid them. For at least for AWS Lambda, we did not see that there was a good way that we could avoid them unless we massively over provisioned concurrency for the function, which kind of takes away from the whole point of it being serverless. And the interesting thing about these cold starts is that they happen more frequently at scale. So if you think about the typical like parallel pattern of traffic that a lot of customers have, when you're scaling down, it's fine because if you have like functions that are already warm and they kind of lose their slots and they go away, that's okay. But when you're scaling up traffic is when Lambda will not have enough functions actually running concurrently to satisfy all of the requests that are coming in which case they will have to increase the number of slots that are allotted to your function, which essentially is a cold start. Anytime that happens, that's a cold start. And what this basically means is that when users are sending you more traffic is when they cannot predict your service response times because you will see like the most latency at that point in time. It just kind of sucks for customers. The other thing is that there are limitations to how much you can scale this. So first of all, there's like an AWS account-wide cap on the number of concurrent Lambda executions. We have with this for customers, needless to say, they were not happy because what ends up happening is this massive retry storm, and it doesn't make the situation any better because there's no way in which you can, in the moment, like do anything about it other than open a support ticket, like increase concurrency limits. So it can be raised, but it feels like a band-aid, and it's only like a matter of time before you shoot yourself in the foot again with this kind of thing. And the other thing is like Lambda is not cheap, at least not at scale. So for Lambda, the cost components are essentially compute seconds that a function runs for and how many requests you've actually sent. But what we've noticed is compute is typically slower on Lambda than it is if you just have a long running service. And so at scale, this would sometimes end up becoming more expensive or just as expensive as our first iteration. So it wasn't really solving a lot of these problems other than if you basically didn't use the function and you just had these environments created at least at extremely low volume, and you didn't have like specific latency requirements, which didn't happen super early. The other thing, as Tecton start thinking about like going multi-cloud, all of these vendor-specific serverless offerings don't actually have parity across clouds. And so if you just look at Lambda, because that's the one that we started with and that we're most familiar with, Lambda has stuff like AWS SnapStart, which is essentially a way in which it can snapshot the in-memory state of a function and then reuse that whenever it has to do like a cold start. And so the theory here is that you don't run into cold start problems that are as bad, but regardless of the specific performance benefit of SnapStart, it is an AWS only thing. And so if we were to try to port all of this real-time compute to Google, we would not be able to leverage that. Similarly, Lambda has this concept of layers, which is essentially metadata that you can embed inside your function and deploy independently. But again, this is something that is Lambda specific. And if you build like a lot of logic on top of this, it does not port quite well. And so like taking a step back, I think philosophically, we learned that for like user-facing latency-sensitive applications, serverless is unlikely to be the solution. Not just Lambda, but just specifically for our use case, we did not think that it was likely to be the solution. Users need predictability and they need low latency. And so if you have highly variable tail latencies, that just won't do. So back to the drawing board we went. And so we started thinking, let's revisit what we actually need. We do want independent scaling of the retrieval service in real-time compute. We want low latency for real-time compute. We want it to be predictable. And so the separate execution environment makes a lot of sense because we want custom dependencies for this real-time compute that users can specify and create. Different permission set also makes sense. And the newish requirement that kind of gets thrown into the mix is it should be roughly cloud portable. And so again, noodled on this a bit, and the conclusion that we came to was we like the separation of running user code in a different compute destination. You just don't like the current destinations. So can we do better? Uh, so we came up with this notion of server groups. And the idea of server groups is instead of running the specific real-time compute workload on AWS Lambda, just run it on EC2 instances on long-running services that are essentially doing the same thing. And you can organize instances into auto-scaling groups. So one function in the second iteration becomes an auto-scaling group in the third iteration. And I'm sure some of you are thinking, why not Kubernetes? So taking a step back, diving deeper into how Tecton is architected, there's essentially a separation of control plane and data plane in the product. And these are two separate kind of AWS accounts, potentially one AWS account and one Google Cloud account, whatever. The control plane account is the one that is owned by Tecton, and that's where essentially orchestration and metadata lives, and all of the control plane APIs. So like the web UI is kind of hosted out of the control plane. The data plane is typically owned by customers. And so they create a sub account in which it is okay for Tecton to run code and run processing that actually touches their data. And so feature data, raw data, all of that stuff lives in the data plane account. And any user code that touches user data should typically be running in this account. And we're kind of moving into this world because we didn't start off in this world, but that's where we are moving to for the large part. And so having tried to do this previously, managing cross-account EKS, just Kubernetes in general, is kind of a nightmare because you are responsible for a lot. You're responsible for running and upgrading not just your user level applications, but the actual cluster itself with security patches and updates, configuration, and all of this stuff. And typically, customers have been extremely hesitant to have an EKS cluster that is running inside of their data plane account that is managed by us. The API surface is huge, and it basically is more complicated than what we need for most of the use cases that we're talking about today. But if you like go deeper into the stack of what all of these cloud offerings have to offer, VMs are actually, great compute primitives. There's a lot of parity across clouds with what they can all do. And they offer a lot of control to us as operators on how we can run workloads that we want to run. And as you can imagine, if you're just running real-time compute services as long-running services, this also lets us maintain ephemeral state. So you can like load stuff and have it be resident in memory and just reuse it across invocations. So, again, the third iteration kind of looks similar where you have your Go-based feature server that is able to now route requests to like auto-scaling groups as opposed to, Lambda functions. And it basically runs quite the same way. So I think we're pretty close to the end, which is great because I just have some numbers to show you. We have essentially two large workloads that we moved. One of them, this is like super simple benchmarks, but we were seeing, so this is the latency that we were seeing on AWS Lambda versus the thing that we were seeing on our auto-scaling groups. The only thing to highlight here is that the P99 that we were seeing on Lambda was like 6 seconds. And the same throughput we were able to achieve like 216 milliseconds on like a single long-running service. Similarly, for some of the stuff at like extremely high throughput, we were able to see a reduction from like 426 milliseconds to like simple workloads on AWS Lambda for Python to 68.9 milliseconds. So that's just how we got there. I'll just talk about some of the lessons because I think this is some of the interesting stuff. I'll just repeat an earlier point here, which is, latency sensitive applications and serverless typically don't mix quite well. Users do need predictability, and highly variable tail latencies are difficult to work with. And taking a step back, I think knowing the specific problems that you're solving for your customers is actually super important. Um, 'Cause customers, like one of the assumptions that we made was, zero ops is like desirable, more desirable than, potentially like variable latency. But this is not true because users will actually manage server provisioning or do whatever they need to do for the problem that they're solving for, which is typically performance. So knowing what you're solving for your customers is actually quite important. The other thing that I think about often now is software systems are essentially always a work in progress. So how can you build in a way that lets you embrace change from what is available for you to use when you're building software, as well as change for what your use cases are seeing or what your customers are seeing and asking you to change in. And I think my last hard-fought lesson is that sometimes the old ways are the best. Kubernetes, AWS Lambda, all of these things are extremely powerful technologies. But every dependency is also potentially a liability because there's just like more stuff to understand, more stuff to configure, which you can get wrong, or fewer stuff to configure, in which case you can't actually solve the problems that you're solving. So that's it by way of content. And so I'm not sure if Q&A is something that we can do.
One of the questions I have is like usually with VMs is that we have this sudden, I mean, let's say we have this sudden burst of requests coming in. Like say, it could be like a flurry of requests which come in like could be at specific times or something like that, so, right? Say, then how
Yep.
do you, I mean, like VMs is tougher to scale up than say
Yep.
Lambda, like how do you handle that?
So that's a great question, and it's something that we have observed. What we've seen is that uh, even for Lambda, if you have like a sudden burst in traffic, where if you go from like 10 to 1,000 QPS, Lambda will also struggle to actually with the cold start problem that I was mentioning earlier, and so you won't be able to make the same kind of like seamless transition to serving that new scale of traffic. Uh, you are right that VMs obviously take longer to scale up. The thing that can happen is that they can accommodate more traffic once they are scaled up. So there are two things that we do. One is we try to make the VM ready time super low, and the other thing is that we allow users to specify like in their provisioning of these server groups what is the min that they need based on like the minimum amount of traffic that they want to make sure that they're scaled to serve. And so you can set like a minimum threshold to make VM startup really good. What we try to do is we try to stuff as much stuff possible into the AMI. So we try to download or do as little logic on instant startup as possible. So if your AMI starts up, essentially your application is ready to go. And we've seen that that reduces startup times to under a minute typically when your VM starts up. But yeah, it is an interesting problem that, aside from throwing a little bit of money at the problem, it's difficult to solve.
I just a follow up. I mean, like I recently came up across this thing. AWS has this thing called warm pools, where they have this.
Yes.
So that is something we kind of like are exploring. So
Yes.
have you tried that?
Yeah. We have not tried worm pools ourselves, although it is something that is on our mind. The other thing is that I believe so. I was looking at the same thing in Google Cloud, and in Google Cloud, you can actually set node settings that say I need to change my auto scaling settings at this specific point in time because I need the minimum to be different throughout the day. But for these 3 hours, the minimum has to be like 10x what the otherwise minimum is. So you can schedule stuff to happen on like a regular cadence also, which is something that I think is an interesting way that you can solve this problem. These are not things that we have yet incorporated into the product, but it is something that we're looking into.
You mentioned that you have this architecture of a control plane and a data plane. I was
Yep.
wondering, like, did you have to, implement much of this yourself, or were you able to use some existing frameworks for that?
Good question. No, I think a lot of this stuff we kind of built ourselves and evolved ourselves. And so the separation of, I know that there are some frameworks that do some of this kind of stuff for you now, but when Tecton started out 5, 6 years ago, it didn't really exist as a pattern that you could reliably build on top of as some kind of open source or otherwise offering. So we had to build it ourselves.
Now, a quick question. Could you have peeled out the Lambda's implementation and started from Firecracker and then built your stack from there?
So we are thinking about this because there are ways in which, so there's a couple of projects that let you run um, uh, essentially firecracker VMs on EC2 instances, and this is something that is actually available to us now. I think one of the big blockers there was you actually need to be running on like some kind of actual physical machine or some VM somewhere. Now that we have sufficient abstraction and a lot of the base architecture exists where you have an actual node that is running that you can run your workload on, it is something that is possible. Um, we did not start off in that way, and so we're still running essentially containerized applications. But this is something that a lot of people in the team are actually excited about exploring to see if that can, improve performance, help essentially node saturation and cost even further, things like that.